So you've memorized the reactions for this chapter. It's just a matter of applying them to specific molecules. And so that's what we're doing here. So you'd look at this carbon chain, you'd see that it has a pi bond. And that pi bond means you're going to be doing an addition reaction. The pi electrons are like extramolecular glue that you can use to add things onto this carbon chain. So what are we adding? Well, that's where you would look at this, at the recipe here above the arrow. And you'll have two steps written in there. And in the first step, you would want to recognize that this is a peroxy acid. So a peroxy acid. In organic chemistry, organic acids tend to be carboxylic acids. These are the acids in fatty acids and in amino acids. A carboxylic acid has a carbon double bonded to oxygen with an OH on one side. And the H is acidic because if this H gets donated as an H+, and the electrons that were bonding to it turn into a lone pair that's left behind with a full negative charge, that's stable because it's allylic to this pi bond. So you could imagine that lone pair waving around as a p orbital that would be parallel with the p orbitals on this carbon and this oxygen that are making that pi bond, so that the negative charge really spreads out over all three of those atoms through resonance. It also spreads out a tiny bit through induction because of the electronegativity of this oxygen. So this is really stable, and because it's really stable, the H+ can get away, and because the H+ can get away, this structure ends up donating a lot of H+'s to a liquid and acting as an acid. So that's what a normal acid is in organic chemistry. It's a carboxylic acid that has this structure, carbon double bonded to oxygen with an OH on one side. Now, in this particular reaction, you're going to have a peroxy acid. Per just means a lot. Like, for example, in the word perfect, if something is perfect, fect means done, and per means a lot. So something that's perfect is really done. It's done as much as you can possibly do it. You can't do it anymore. It's perfect. And so peroxy means a lot of oxygens in your organic acid. So if this is your normal acid, and this is sometimes abbreviated, this is sometimes abbreviated as COOH or even CO2H, if that's your normal acid, a peroxy acid is going to have an extra oxygen per a lot of oxygens. And so you fit another oxygen in that area. And this can be abbreviated in a few ways. You could have 3 O's and an H. You could have CO3H. These abbreviations tend to be more common in standardized tests because they don't have the software, or they don't want to use the software in printing space that it takes up to draw the whole structure out. So that's how you'll recognize a peroxy acid. Now notice, carbon can form 4 bonds, and I have not indicated here what the other bond is. It could be anything. And so if you remember, in organic chemistry, any carbon chain is represented by a capital R, kind of like an X in math means any number. So that could be anything. So in this particular case, it's a really short carbon chain. You're looking at that end, you see those 3 oxygens, and you're like, oh my gosh, that's a peroxy acid. But it could be anything. I could add carbons there, I could add rings, it doesn't matter. All you need is a peroxy acid. So that's what you're looking for. The most common peroxy acid, or one of the most common, is something called MCPBA. Stands for metachloro peroxy benzoic acid. This name will make sense to you in organic chemistry too, but for now, the structure of that looks like this. So you could see you have your peroxy acid on one end there, and this can be anything, right? in the case of MCPBA, it happens to look like this. But one thing you might remember is that MCPBA is a peroxy acid. So in this particular problem, they give you two things. They give you the peroxy acid in one step, and then an acid wash in the second step. And so what you want to do is you want to see those two elements and see that this is anti-dihydroxylation. And these long names are really descriptions that are being used as names. So when we think about what we're adding, where we're adding it, and how we're adding it, that name really tells us a lot of that information. Dihydroxylation. A hydroxyl group is an H and an O. Hydrogen, oxygen. So hydroxyl group. So we're going to be adding two of those, dihydroxylation. And we know they're going to be adding anti. They will be adding on the two carbons in the double bond. We don't have any rearrangement, so we don't have to worry about any of that. They're the same group, so it doesn't matter which group goes to which carbon, because they're the same. And just note that if you do have a chiral center, you'll form a racemic mixture. So, like we've seen before. So with those things given, we can apply them to this particular carbon chain, and you'll look at those two carbons in the double bond. That's where your OHs are going to go. There's no rearrangement, so one OH will go on one of those. The other OH will go on the other. And in the process of doing that, we'll use up those pi electrons. So that pi bond won't still be there. So we erase that. Now, we do have a chiral center here, so it's important that we draw the direction of the bonds. And I'll just draw both of them. And because this is anti-dihydroxylation, one of these OHs will be coming out at us, the other will be going away. And we'll have a racemic mixture where the directions switch. So the one that was coming out at you will now draw going away. The one that was going away will now draw coming out at you. And you would end up getting both of those products in this particular reaction. So this top carbon is technically not chiral, so you technically don't have to draw the three-dimensional arrangement there, but you do have to draw the three-dimensional arrangement at the bottom. And just to help you visualize what's happening, it's nice to have them anti. Let's just sort of take this thought process and apply it to another molecule. This example here, yet again, you would look at this, you would see the pi bond, and you'd think we're doing addition. What are we adding? You'd see two things. The first thing is a peroxy acid. You'd recognize that by those three oxygens there. And the second thing is an acid wash. And when you see those two things, you think this is a anti-dihydroxylation. So we're going to be adding two OHs on opposite sides, and if we have a chiral center, we'll have a racemic mixture. So we'll look at the two carbons in the double bond. That's where the two OHs are going to add. We'll put one OH on one carbon, the other OH on the other carbon. In the process of adding them, we're going to use up those pi electrons, so those won't still be there. And anytime you have a ring, you have to make sure you show this anti-configuration. And so here we want to show that one of these OHs is on one side of the ring, the other OH is on the other side of the ring. But we have chiral centers here, and so we'll get a 50-50 mixture of the two enantiomers. So in the other enantiomer, that left OH would be going away, and the right OH would be coming out at you. The last thing you have to fix here is this methyl group. The carbon that it's on is tetrahedral, so it needs two bonds in the plane, one coming out at you and one going away. So if the hydroxyl group is coming out, that methyl group will have to be going away. Likewise, if the hydroxyl group is going away, that methyl group will have to be coming out. And so those would be the two products you would get in this reaction. Hopefully that gives you some sense of how you would approach these anti-dihydroxylation reactions in a one-step synthesis where they give you all the reactants.